on the air calling CQ 20 meters.
We're here in Rock Hill, South Carolina. My name is John Gendron, NJ4Z. I'm the current president of YCARS, and we're doing a presentation this evening on emergency communications and the use of NVIS antennas. We're also going to talk about design of NVIS antennas. So welcome, and I hope everybody's doing well and safe in these uncertain times. We'll go right into the meat of this. The presentation itself, some of it was garnered from a presentation given by the South Carolina section manager, Dr. Mark Tarpley, N4UFP. He gave this presentation a few years ago. I garnered some of the information from it and took and added in some emergency communications platforms and some scenarios into this so that you can see the real use of NVIS on an everyday basis. It's meant as a primer for emergency communications. So basically, we're setting up a scenario here for emergency communications. I'm the EC for York County Aries, and we're in the Charlotte metro area, Charlotte, North Carolina, basically we've just experienced a very large ice storm taking out commercial power, all cellular towers, internet service. Regional roads are impassable. We've got 7 to 10 days more of the ice and snow coming, and we've got people trapped in homes, businesses, and facilities. Local repeaters and public safety repeaters are damaged, and the basically communications are down. So they're bringing in Aries to help pass traffic on the amateur bands. So emergency communication methods, what we typically try to do is use UHF, VHF. And for local stuff, because it's FM and digital, the very clear modes. The robust and local regional emergencies, we can use those pretty wholeheartedly. They're low cost and very portable equipment, and you can send text, voice, data, photos, and video over those links. Also interoperability between the 2-meter band. UHF and VHF, the disadvantages depend upon local repeater for regional communications. The line of sight is difficult in mountainous terrains or in cityscapes where you have a lot of buildings, and it's limited power on the handhelds, so you won't get as far. When we talk about direct line of sight, as you know, with HF you can bounce that off the atmosphere, not so much with UHF and VHF. So basically, you've got a formula there that shows you what the distance is for line of sight on the horizon for line of sight transmission of radio waves. Basically, what happens if you have line of sight obstructions, mountains, buildings, if you're in a valley, the signals bounce off. So at that point in time, we would use repeaters to send a signal from point A to point B around the mountain or over the mountain, whatever the case may be. So you can use UHF, VHF and have relay stations that are out of that path and go around the obstacles. You could go satellite, very expensive and very expensive gear, or you can try HF ground wave or HF NVIS antenna communications. Now NVIS stands for Near Vertical Incident Skywave, and basically what is it? Is you're going to use your antennas to radiate the RF signal from your radio at a very high angle in an appropriate frequency, and it'll bounce back down kind of like an umbrella into a local area coverage or regional area coverage, versus what we're usually looking for as ham operators going out to reach out and touch somebody DX, using low angles of radiation. It's not a new propagation method. It's been around for a long time. The Germans used it in World War II. The military used it in Vietnam, and they still use it today. A lot of times you'll see the Hummers or the MRAPs going down the road. They'll have those very long antennas on them, and they're bent over the vehicle and weighted down. Well, that's not because they don't want them up riding high. They want to use that antenna in that configuration so that when it's curved like that, the radiation is going up instead of out in a omnidirectional direction. Many amateurs use NVIS on 80 and 160 without knowing it. Why are they doing that? Because their dipoles are too low. You know, basically for DX communications, you want to have your dipole quarter to half wave up or a little better than that. Well, on 80 meters, that's 120 feet, thereabouts, 128, and if it's 160, you're well over 200 feet in the air to get that quarter wave. You know, if you've got a 160 dipole at 80 feet, you're using NVIS. Same thing with 80. If you have it much lower than, say, you know, 100 feet, yeah, you're using NVIS to communicate. How it works, the key to this process is the antenna and the type of radiation angle that you're using and the critical frequency. So the critical frequency is the highest frequency which the F layer of the ionosphere will refract at a maximum of 90 degrees. So if we're launching straight up, we want the frequency that the F layer is going to bring right back down to us. Again, you want to be higher than 70 degrees. And the RF is below the critical frequency, so it'll be refracted back to the Earth's surface. Because the RF is launched at near vertical angles, it returns back to Earth within a 1 to 300 mile range. So normally we're looking at skip zones when we're using low angles of radiation where your RF is launched and it skips over a large area before it refracts off the atmosphere, comes back down, and is received or skips again, and you get that what we call a skip zone. Now you'll get RF ground propagation for a short distance from your transmitter or your antenna, and then you have the skip zone, and then you'll have another zone where they'll be able to hear you again. With the NVIS, you're going to shoot that straight up in the air. It's going to come right back down, and you're going to have a wider area of coverage regionally versus having that skip zone and then DX. Attenuation on the path is less than what you would have on low angle radiation because you're taking a shortest possible trip. So basically you're not doing multiple hops like you would with a DX. You would be a DX launch at say 25 degrees or 10 degrees or 11 degrees, whatever. You have that long path, so you're attenuating that signal every time every time you skip and the further you go away from the transmitter. With NVIS, because you're going straight up and straight back down at a very short distance, you're not losing any of the signal to attenuation. And basically this next slide shows you the NVIS 75 to 90 degree launch angles, and then you see DX at less than 30. So kind of gives you a little more visual reference to what I was explaining. In order for NVIS signals to return to the Earth's surface, frequency must be less than the critical frequency. Daytime, that's typically 5 to 15 megahertz. After sunset, the critical frequency drops down to 1 to 5 megahertz just before dawn. It's desirable to use these frequencies to minimize the absorption by the D layer. Okay, so basically during the day, you want to stay on 60, 40, and 30, and at night you want 60 and 80, and that's when you have good solar activity. And when we have less solar activity like we do right now, you're looking at daytimes of 80, 60, or 40, and nighttime of 80 and 160. Now 40 will work some in the evening, but once you get much past, I'd say midnight, you're not going to get much refraction off the F layer of the atmosphere at 40 meters, so you're going to be looking at 80 meters. But it works fairly well. The other caveat to NVIS is really you need to have both antennas set up for it. Now, it'll work some with people being an NVIS antenna and a normal setup antenna, but because the radiation is coming down at a high incidence angle, sometimes a normal antenna setup won't receive very well on NVIS. But you get good coverage from ground wave prop about 25 miles, and then you move out to about 300 miles is about the maximum you're going to see off of an NVIS propagation via the atmosphere. Let's go to the next slide here. All right. Advantages of NVIS. So one of it is noise reduction. It's not very noisy at all. Because you're looking straight up, you're not getting all of the electrical noise and all of the other RF that it can interfere with our signals. So you get a very clean signal. You can transmit CW, voice, email data, photos, and digital propagation over that. It doesn't require high power. One of the advantages is when you use NVIS, because you're launching at such a high angle and you're getting reflection off of the Earth, a lot of that signal is focused in one direction, and that's basically straight up. So you get this high lobe gain of bubble of RF off your antenna. So 50 watts is plenty to reach out in that radius zone of 300 miles, no problem at all. In fact, you'll probably be a lot louder than the DX stations coming in. Because of that phenomenon of pushing all that RF up. And you can use a small number of stations because that zone is so compact and regional. You can use a small number of stations and cover an entire state or entire region, tri-state area, like say you were in New York. I mean, New York, Pennsylvania, Eastern Pennsylvania, New Jersey, Connecticut. You can cover those fairly easy using a NVIS network. And you can set these things up rather quickly. It's a very simple setup. The antennas are very simple. Most of them are dipoles, maybe some loops, but very simple to set up. Don't take a lot of people. Doesn't take a lot of support. So it's a lot of very agile communications ability there. NVIS operation, so prior planning is important. So you need to have a plan for what frequencies you're going to operate. You need to know your equipment too, how to set it up, how it works, and you better practice with it so that if an emergency comes, you know how to operate that equipment, you know how to set it up, you know what to expect, and where to go to join your local nets. Now in South Carolina, being the EC, I was able to get a copy of the plan here for our region, which we're in Region 2 of the upstate of South Carolina, or the Piedmont of South Carolina, however you want to say it. And during the winter, we run our local nets on from midnight to 8 a.m. on 80 meters, alternate is 160. And then during the day from 8 o'clock in the morning till 1600 in the afternoon, it's 4 o'clock in the afternoon, we're going to run on 40. And if it's not good, we'll run on 60. And then later in the day, we move back down to either 60 or 80. And then in the evening, we run primary on 60. And then the alternate is 160 again. And then if during the summer, because 160 can be a little bit noisy, we can press those options down, and you can see the options. We run 80, 160. We run 60 or 80, and then 80 and 160. So once you have your frequencies established, then you set out your plan. So you know what frequencies you're going to run on. People know what frequencies are the alternates. And if you have to move, you make your move to the alternate frequency, and then if the band conditions change at a quarter-hour intervals, you go ahead and check the other bands and make sure that you find an established communication band that'll work. Operating frequencies other than 60 meter band can vary by 10 kilohertz, and 60 is a segmented channelized band, so you only have 5 places to interact there, and you have to stay within those 5 areas. You can't move up and down. Also, your peak to peak power is 50 watts there, and you're only allowed to use upper sideband on 60. Okay, so let's talk about assembling a station for NVIS communications. Standard 100-watt radio is fine. If you run a mobile radio, say an 890, Yaesu 891 or an 857, or even the 897, an older radio, or a ICOM 7100, you know, something similar to that, 7300 ICOM, you know, it's a small radio, very portable. That'll work just fine. Don't need power amplifier or any of that. A built-in tuner or a small tuner does help in case your dipoles are not resonant where it needs to be. But most internal tuners will tune them with no problem. And you've got to design it to run at a very high angle, launch angle. You don't, I guess the best way to put it is you don't want these antennas high. You want to run them low to the ground, but you won't want them too low to the ground. Mounting height is between 1/10 of a wavelength and 2/10 of a wavelength. So we want it under a quarter wavelength, but not lower than that 1/10 of a wavelength, because what happens is you start to get interference with the ground. The ground will play havoc with the resonance of the antenna, and you'll get a lot of reactive components onto your resistivity of the antenna, and you'll end up with high SWRs. And again, your feed point impedance will be all screwed up again. Your SWR will be messed up there. The antenna is erected typically in an inverted V, and again, less than a quarter wavelength, and you want to keep people away from the ends of that antenna. As we all know, a dipole antenna, at the feed point, it's high current. At the end point, it's high voltages. So we don't want anybody at the ends of those antennas when we have high voltages present. So this slide basically gives you and I'm going to have to put on my glasses for this one, I apologize. The height above ground in wavelength along the x-axis and the y-axis is the max gain. If you look at going at a quarter wave above, you're looking at about 6 dB a gain, 6 dBi of gain. So we want to, you know, gains bananas. So that's against a isotropic isotropic radiator. So basically a point in space, perfect radiation. You're going to be 6 dB better than that. So if you were to compare it to, say, just a standard vertical, at a standard vertical, you're looking at negative 5 dBi of your transmitter output power. And so when you operate in this particular configuration, low to the ground, with a dipole, inverted V, because all that RF is focused up, you're going to be looking at about a 6 dB gain there. So you're an 11 dB gain over a standard vertical antenna. So that's why I'm saying low power is really, you can use low power. High power doesn't have any real effect with these type of antennas. The other thing you want to look at, the chart below that gives you your takeoff angle in the vertical and the height above ground in wavelengths on the x-axis. So if we look at 2/10 of a wavelength, you can see we're at about 90 degrees radiation. So I would be somewhere between, for me, somewhere between that 2/10 of a wavelength to a quarter wavelength, because if you're going straight up and down, it really does limit you a little bit on how far out you're going to propagate. I would rather have my launch angle somewhere between, let's say, 75 and 80, 85 degrees. That's going to give me a little better coverage because the ground prop's going to cover that hole from 90 to 85, say. I'll have enough ground propagation to cover that hole, and that gives me a little better of a coverage model per se. So, construction of NVIS dipole. Typically aluminum or copper wire. THHN is fine if you want to use, you know, fence wire, if you want to use, say, 13 gauge antenna wire, silk wire, anything like that, it's proper. You just have to make sure that when you are cutting your antenna, and I've given you some lengths of dipoles down there for each band, you have to make sure that if you use an insulated wire, that you allot for the velocity of propagation in that wire. So when we talk about a bare copper wire, your velocity of propagation doesn't change. So you can use those measurements at 65 feet 11 inches for a 40 meter dipole. If I were going to use that insulated wire, I would multiply that length by about 0.93 to 0.95 and shorten that antenna just a little bit. Because of the insulation on the wire, it changes the velocity that signal radiates off through that wire. So you want to be cognizant of that. This is a typical dipole construction for 80 and 40. So you use the same feed point, and you're going to do an inverted V, and you're going to basically, it's a fan dipole, but what you do is you fan them out at 90 degrees to each other. So you've got 40 running in one direction and 80 running in 90 degrees offset to that. Very simple to put up. You can build these inexpensively. DX Engineering up in Summit County, Ohio, builds a very nice NVIS antenna kit that you can put together. They give you a 15 or 18 foot mast, the 1-to-1 balun, and the wire, and if you want to shorten the 80 meter radiator down to the same length as the 40, they have some loaded coils you can add in. And this is a picture out of their instruction book of what their antenna looks like from an aerial view. So basically you have the center of it having your 1-to-1 balun, and then you have your 40 and 80 legs coming off of that. And again, a 80 meter radiator is going to be about 80 feet on each side. You can shorten it to where a 40 is if you use loading coils on that. And so again, they make a really nice kit. I've kind of designed one that I built and have tested, and it works fairly well. And it's a very similar design to this, but I used a 7 meter soda beam pole. Collapsible, that collapses down like 21 inches, very lightweight but heavy duty, enough to hold the LDG 1-to-1 balun that I got. And I'm using DX Engineering's very small, I think it's like 24 or 26 gauge antenna wire. They call it their stealth wire. It's pretty cool stuff, very lightweight but very robust wire for antennas. So that may be an option for you to try out. So multi-band operation with dipole, again, we talked about that bubble of RF. So this is a visual representation of that. So instead of having that radiation going out low angles, we're going to force all that radiation up. And when we do that, it creates gain, because you're taking, you can't create gain in one direction without giving it up in another. So what we're doing is we're forcing all that RF to focus up, so we get gain because we're taking all of the radiation in one direction. And again, that gives us several different options, whether it's 30, 40, 60, 80, or 160, and you can see the different gains. At 30 meters, that chart is showing us at straight up and down, we're at 8.55 dBi of gain. That's a lot of gain. So if you follow the rule of 3 dB doubles your power, so let's just say we're using 50 watts. So the first 3 dB, so now we're at 100 watts. The second 3 dB, which gets us to 6, gives us 100 watts. The next 3 dB, which would be 9, so we're just a little under that, would be close to 200 watts. So we'd probably at 8.55, we're probably somewhere between 155 watts and 170 watts of effective radiating power out of a 50 watt radio signal, minus the loss in the coax. So you can see where low power works really well for NVIS. You don't need a real high power radio, don't need an amplifier. You can do very well with even QRP radios at this, because if you look at 5 watts, 5 to 3, that's 10, 3 more, that's 20, so now you're close to almost 40 watts of radiating power in a very short distance. So it's a unique opportunity to leverage very low cost radios, even QRP radios, for this kind of thing. And those are lightweight, small battery consumption, really good for field work for emergency communications. And you can also talk about loop antennas. And I've not tried a loop antenna for NVIS, but my guess is it's going to be very similar to a dipole, although you may have a little better radiation pattern off of it if you're looking at from a plan view versus an overhead. My guess is you're probably going to have more of a figure 8 tile style radiation pattern with a dipole, versus with a loop you're going to have more of an omnidirectional pattern but forced up, so it's going to look more kind of like a mushroom than a dipole would. Again, full wavelength, you want to run it just like you would a DX loop, but you're going to just shove it down closer to the ground. Some people call them cloud warmers, if you've heard that term before. Ideal height, again, is about 1/10 of wavelength, but not going over 2/10 of wavelength. That's the difference here. If you go below 1 wavelength, you're going to drop off, and you want your input to be somewhere between 70 and 140 ohms, so you're going to have to use a different style balun or a matching stub in there. And again, if you look at the height over ground versus the takeoff angle, as you can see, you start to drop off there very quickly after you get to 1/3 of a wavelength off the ground. And I've got a next slide that kind of shows you the radiation bubble for that from a plan view. As you look at it, you can see you can feed it with coax or ladder line. For me in the field, I would much rather have coax. It's a lot easier to deal with ladder line. You don't have to have the tuner there or another balun, a second balun to match it into your radio. I would much rather deal with the coax. Again, you're going to see that 0 dBi or 7 dBi gain there on the 60 meter, and it's very close on 80 meters. 40, it bends down a little bit. Again, that's probably more of a deal with the length of the loop than it is anything else. But if you put an 80 meter loop up, you're going to be looking at these kind of radiation patterns. And you can run it either horizontally or you can run it vertically. Again, vertically is going to change the propagation just a little bit. Again, we want that takeoff angle close to 90 degrees. And as you can see, it flattens out the 40 a little bit. You don't have that dip at the top, but still not as much gain, but still a very robust antenna. Depends on how critical it is. If you have a mass support, I would go with a dipole. If you have the ability to set up 3 mass, I would probably look at a horizontal loop. And if you've just got 1 tree, you could run a vertical loop, but at that point in time, why not run a dipole? It would seem to be a better gain, other though your radiation pattern is going to be a little different. So mobile and portable antennas for NVIS. Inverted Ls, yeah, low to the ground, that would work very well. 2 loaded fiberglass whips or ham sticks, basically making a dipole, that would work fairly well. Antenna systems like Alpha and the Chameleon, Buddy Pole, those all have some NVIS properties, especially the Alpha vertical. I have one of those, and they actually have an NVIS element to that antenna. So if you've seen an Alpha, what they call their full metal jacket vertical, it's a no-tune antenna, basically a loaded coil with a 13-foot whip that's expandable on the top, and then it runs out a 25-foot NVIS wire off of that same connection point as where the whip goes in, and then it's a grounded antenna. So that does provide you some ground propagation and some NVIS characteristics off that antenna. It's a neat one to take if you don't have any ability to support an antenna. It comes with a tripod, so it works really well. Same thing with the Chameleon. It's a very similar style setup. I think their MPass is their MPass 2, maybe their setup that runs very similar to that Alpha. And then Buddy Pole has some different things, and I'm not as familiar with their product. And then, of course, you have the DX Engineering NVIS system that they sell, and then Bushcom. They're used by the military. They're really good antennas for NVIS, but fairly expensive. So if you run into a somebody's going to run into a Bushcom antenna, they've put some serious money in their system. Alpha also built some stuff for the military on a carbon fiber platform, which is pretty neat, but again, it's expensive. And you've got to make sure that you keep these things, away from things as much as you can, so that you get a clean propagation path for the antenna. You can use metal. I mean, a gutter on a house would work too. And sometimes you have people put another wire underneath the dipole to give it a little more gain. But I'm not sure from personal experience that's worked, but that's been anecdotal. I've heard that works pretty well. So in summary, NVIS is a mode that many answers use without recognizing, especially on 80 and 160. For e-com communications, for simple, whether it's voice or CW or even some of the digital modes, you don't need any specialized equipment. You don't need amplifiers, and it's a very simple portable system, carryable. Take it out in the field with a dipole, very simple inverted V dipole. And you have an NVIS, a possibility of doing NVIS communications. And if you're involved with Aries, it behooves you to have something like that set up, that if you are a deployable asset, that you're able to do NVIS, because we may not be able to use UHF, VHF. We may not have enough relay stations. So it's something to consider, and like I said, they're very simple to build, very robust regional coverage, and it should be part of your toolkit. So at that point, I'm open to any questions if we have any. I know it's a little bit shorter presentation than we normally do, but it's a very simple subject for that matter. Do we have any questions regarding this? No, none at this time. Well, thank you very much for your attention this evening. Glad you could join us. If you have any questions, feel free to reach out to me, nj4z@yahoo.com. I'll be glad to answer any email questions you may have. I also do want to note that for our club members who are watching this, who may have not been on the net or haven't been to the Facebook page, we had a very successful food drive for the Y-Cars Cares group. We provided 1,300 pounds of food to Pilgrims Inn here in Rock Hill from our collection on Saturday, April 25th. And we also raised an additional $500 in cash from very generous donors that we had given to Pilgrims Inn. So thank you all for that. And again, please be safe and stay healthy out there. Look for more from us from the Y-Cars group, and from all of us here in South Carolina at Y-Cars, and especially from me and J4Z, 7-3 and good evening.
Parks on the air calling CQ 20 meters.